Okay, good afternoon, everyone. So please scan your attendance. Just now I already shared the data for your test two. We'll do it on 24 May lah, on Monday lah. Because I'm not too sure if you have class at 3 p.m. or not. That's why we'll start a bit early, 1:45 to 2:45, and then 15 minutes to upload lah. Okay, to upload by 3 p.m. lah. I wrote there wrongly. It's actually 3 p.m. So we 1:45 to 2:45 and then 15 minutes. What will be covered is the whole chapter 4 and then 5 definitely, and then 6 is this one. Uh, and then if we manage to go to chapter 7, then we include that as well. So it will be 4, 5, 6, 7. Okay. So in this chapter, we'll be learning about chapter 6, non-equilibrium access carrier in semiconductor. So when students come across this chapter, they find that the equation is slightly difficult because there is a lot of derivation explained in this slide, but I don't really ask derivation in the test. So I perhaps this time around, I will ask more about comprehension and also discussion, more or less on that lah, justification from this chapter lah. It's more like theory lah. So if you look at the title here is non-equilibrium. Okay, so in chapter 4 you learn about equilibrium, which is you get the NO and PO, and then you go to compensated. But here is non-equilibrium. What it means by non-equilibrium, which means that it is not in equilibrium state anymore. You apply something like heat or electricity, there is a movement. So non-equilibrium will happen. And in this state of non-equilibrium, you will create additional carriers. Okay, what you learned before, it was NO and PO only, right? Now you got excess carrier, like delta N and delta P. So this excess carrier contribute to the carrier movement in semiconductor. So you discuss about the behavior of non-equilibrium electrons and hole, concentration as a function of time. This is based on ambipolar. In the end, you get function of time and also coordinates, space, time and space. So before you can start, you need to know this term here. There's a lot of term notation, which is the carrier generation and recombination. You generate, after that, what he meant by recombination, which means that it dies, it's alive and then it dies, then regenerate and recombination. So generation is the process whereby electrons and hole are created. And when electrons and hole are destroyed, then they call recombination process So it's alive and die, it's a cycle like that. So created and destroy. So in thermal equilibrium, we have electron breaking out of covalence bond due to acquisition of enough thermal energy to hop from the valence to conduction band. This create a free electron and a free hole. Okay, in thermal equilibrium, this is like so if you have enough thermal energy, you can jump from valence band to conduction band. Then you create a free electrons and hole. And then if you lose your energy, then you drop down to valence band. So by the same token, there are free electrons that lose some of the thermal energy. Then they encounter a hole and fall back into covalent bond. So this is regeneration and recombination. So this is actually taken from Neumann's book. So you have enough thermal energy, you jump from covalent, maybe you jump for valence from valence to conduction band. So when you jump, you create two things. It is actually the same thing. Hole is the absence of electron. Electron will go to the conduction band and suddenly hole will appear here because hole is the absence of electron. Then if you loses your energy, the next thing happen is you recombine again. The electron will fall down into the valence band and there's no more electron here. and then the hole will disappear. So for thermally generated free electrons, they must come in pair. If you have this G here, recombination rates, generation rates for electron, it'll be the same for hole. Okay, because they comes in pair, and when they recombine, they could recombine in pair. Then the problem comes in the later chapter, in later section, where sometimes the G is not same with G and R is not same with R, then that is what they cause a confusion. But here in theory, now is everything the same. This one is the same and that one is the same. Okay, we got the big capital G and big capital N. And then they got the word, the notation, the subscript here is the small letter N. O is a not means that original. Then it's a P naught, then you see lah, this big capital R, and then the N naught and P naught. So in thermal equilibrium, you put everything is the same. Generation rate is the same, recombination rate is also the same. In thermal equilibrium, the total number of free electrons and hole is constant, so the rates at which they are being generated must be equal to the rate at which they are recombining. Now it comes to these two things here. This is the new one. Access carrier, because before that it was all normal. This one you already know how to calculate from chapter 4 and O and PO here. This one okay. This one is okay, but this is the new thing here. And you can see that they got a delta N and got a delta P here. So in delta N and delta P for SS, right, they're using small capital now. Small capital, and then there is a prime here. This is a prime here. So this prime means that access lah. This is what the indication access here. So external event, okay, external events such as photons can disrupt the equilibrium through, this is spelling mistake, through, not draw, through creating additional electrons and hole pair, okay, through creating, typo here. This excess charge carrier will be generated at equal rates for electrons and hole. So now if you have photons, and what they do is that electrons say, oh, photon, they absorb the photons, they have extra energy, then they'll jump to the conduction band. Okay, so now creating delta and excess carrier. In addition to the thermal equilibrium that we calculated before, now we got the new delta N and delta P, and that is shown by this small capital G prime N equals to G prime P. So now you can say that now this is the NO and PO that we calculated in chapter 4. In chapter 4 here, this is chapter 6 here. Don't know why I put the line here. Now you got a new one they call N and P. There is no more O or anything here. It's N and P. So N and P now is the number of actual excess electrons and holes are Dn and Dp. The total number of free electrons right now, free electrons and hole can be now written as, you have to plus with this delta and PO plus with this delta, and then you get the total number of free electrons and free holes. So the excess electrons and hole will be recombined in pairs, so we write them in terms of this. So the confusion come here again. You see the G right now, Newman's book, they use a small capital G. And then for the R, right, they're not using small capital R, they use big capital R, but the only thing that to differentiate it is the prime here. The prime will show you how it differentiates. So it's the same thing like going down here, you got the R, you got prime is SS, and then N equals to R prime P. Now, this is the new thing we need to calculate. This is the one that low level injection. So the low level injection, please open your WhatsApp and read it. What do I mean by low level injection? So in your WhatsApp, it's written that the majority carrier is not affected significantly. There is a disturbance in the equilibrium state. So you're going to have excess carrier, but the excess carrier is extremely small compared to your thermal equilibrium NO and PO. so it doesn't really affect your majority carrier. So that what it mean lah. So this is again for all those things. If you find it that you don't really understand what I'm explaining, again, this is a summary of what is written in Neiman's book. So best suggestion is after this, if you don't really understand what I'm explaining, go and read Neiman's book again. It's very long. It will provide a lot of information. Getting back here, you see what is excess carrier. Okay, there's a model here. A simple model of recombination. We are using direct bank-to-bank recombination. So now they created this dNt over dt. Okay, so this is called the net rate because it's against time here of change in the electron concentration, which means that how much does the electron concentration change with respect to time. Okay, with respect to time, how much is the net rate of change? It's already perubahan change in the electron concentration. So this equation is given here. So what is the equation? Let's look at it. So Ni squared, we know that Ni squared is NO and PO, right? So Ni squared minus with Nt multiplied with Pt. So this is, what is this equation? It's shown here. So this one is NO plus delta N and PO plus delta P. But now with respect to time and time here. Okay. So they say that the intrinsic minus with this with respect to time. And let's say if you multiply them into this alpha R here, you multiply inside. So this is what I'm going to explain later on. This is how you get this equation. Let's get it back. Then you get this alpha Ni squared is called the thermal equilibrium generation rate. Okay, this is what you find. Then note that the entire expression in the parentheses will be less than or equal to 0 so that the derivative is negative. This should make common sense as NT is decreasing due to recombination. So NT is combination. Okay. Since NO is constant with respect to time, the derivative can be taken with respect to dN instead of N. So this is actually assumption that they use to reduce this expression. Okay, so they say if with respect to time, then you can cancel it. So let's see here. So you multiply them to this one, you expand them. Okay, this equation you put in, expand them, and then you multiply you multiply with them. Then what do you get? So in this stage here, you will get Ni squared minus NO and PO. So you cancel each other. This one you cancel. Then you'll get negative NO dP here, this and that. So you copy down here 1, 2, 3, 4, and the negative sign you bring it forward. Okay, this is what I did until here Negative sign, bring it forward. Then what else you can take out? You see that each of these components has a delta n, so you take out the delta n as well. Take out delta n, put it down here. Then in the end, you get the NO plus PO plus delta NT. And then this delta NT here outside. Okay. So you can simplify that further. Okay, here, by applying the low level injection here, we will try to simplify them. That's the purpose of doing this. You simplify them. In the end, okay, what we do here, low level injection, if you assume that, then you can say that, so like I told you just now, right, in the WhatsApp, right, we means that the excess carrier is much smaller than the majority carrier. So we know that this one is smaller than PO. Okay. For P material, for P-type material, you're gonna have excess uh, electrons and excess hole, and this one is excess electron. You say, okay, for P-type material definitely is less than the majority Majority is PO, then definitely smaller. And another thing is that NO is also smaller than PO because it's a P-type material. So therefore, you can written as this one, this term here. The term here multiply. So this is going to be a lot, PO here. This one's going to be small. This is going to be huge. And this is going to be small as well because you know that the delta N is small. So you can cancel them because small and multiply with small, you get very small. And then here, you know that NO is also small, delta N is also small. You can cancel each other. So you see, by doing that, in the end, they already simplified this term here. We can see that the term delta N PO term will dominate compared to the other two of the right hand side of the equation. We can approximate this equation to this equation right now. So now they say that, okay, we go to here, then we move on to the next slide. The solution to this equation, okay, now this is like what we call the, you have to do some integration here to solve it lah. So the solution to this equation, what kind of equation can delta nt be so that when you do a derivative, you get something like that. So they said that, okay, it has to be an exponential. So this kind of solution to this equation has to be exponential. Okay, so now they start with this exponential. Okay, just bear with me. And then you got this initial state here because you have gonna have a constant. You put 0 here. Okay, then TNO is the excess carrier lifetime given by here. And the solution to this equation here, they say that must be in this kind of exponential, correct? And they have to have this component where you have this alpha and then you P not T. And then they say this one, we can simplify them into T over tau not, tau N. Okay lah, so what they do is that they solve it lah. Once they solve it, and if they done it, they say that, okay, this equation that we're going to solve, this one, we're going to solve this equation, is actually called the excess carrier recombination rate. R prime is the change of number of excess carrier. So we can return it as the most difficult one that we solved just now is this one, is basically is this. And then you put it down here. Okay lah, it's actually the delta N over tau. So that's how this get this equation here lah. The R, if you want to calculate the recombination rate, is actually a delta N over tau N. Okay, so by getting here, I mean that you find that there's a lot of information going on here. All right, so and we haven't even do any calculation yet. So student, when they come to this part here, this is only the beginning part. They find that uh, maybe because I explained the derivation step, and derivation step is a lot to take in. That's why you don't really know what's going on here. So let's open Neiman's book. Let's see. Okay, now I'm open Neiman's book. Okay, let me share. Okay, so this is the Neiman's book. What I explained earlier on. Okay, this one is the access carrier. Okay. That this is the one that I'm showing earlier on in my slide here. So the first term, A alpha and I square, is the thermal equilibrium generation rate. Okay, generation. Access carrier I created in combined pair. That's why we have dN and dP. Okay, this is the same. So we can use this. Then over here, this one 6.9, they directly from here, they jump to this part here. And I prepared the slide over here to explain how did they get from the top to the bottom lah. How did they solve this? Because in Neiman's book, they already say, they just say that, oh, here, jump. Okay, then you say that if you impose the condition of low level injection, so low level injection put the limit of magnitude of excess carrier concentration compared with thermal equilibrium, which means that the excess carrier on is extremely small compared to NO and PO. So you say that if you have an N-type material, then N is more than P. And then if you have a P-type material and P is more than N. Okay, low level injection means that the excess carrier concentration is much less than the thermal equilibrium majority carrier concentration. If you have a high level injection, which means that your excess carrier becomes comparable or greater than the thermal equilibrium majority concentration. So after that, it say if you compare a P more than N, so this equation here, they try to cancel each other. They cancel. Just now I show you whatever that they cancel. They say that, okay, we already got equation 610. And what is the solution to this equation? Okay, this is something like a partial differential equation here. Then they say it has to be exponential and it has to be this term here. They say, okay, then we try to solve it. And once they solve it, they say that, okay, the one that we solved earlier on, this part here is actually called a recombination rate. And given by this equation, when you solve it, positive here, and you can, in the end, you'll get something like R and recombination rate for excess carrier is delta N. Okay lah, makes sense lah. Delta N is the excess over tau lah. T or tau here. Okay, so just go back and read again this thing here that I explained in this slide here. Nothing, not difficult lah. First time maybe you don't really get it. Okay, then there's some exercise here. Okay, there's some example here. Let's see some example here. Consider silicon temperature 300. We have donor impurity ND. Then the excess carrier lifetime is 2 times 10 to the power negative 7. So now this question here is that are they getting excess carrier or they are getting normal concentration? If you look at this question here, they are not asking about excess yet. So excess is part B lah. Part A is not part A is only holes. It's not talking about excess hole. Part B is talking about excess carrier. They're giving you the delta N and delta P. So what is the excess hole recombination rate for this condition? So how do we solve it? So the first part here is that, like I say, it's just like a compensated kind of equation here. So we say that Na is not given. So, okay, Nd is equals to 5. Then you use this intrinsic concentration, Ni squared divided by this Nd, you get for PO. So now you got these two terms here. You got NO and you got PO. Now it's saying that, okay, now you want to calculate the carrier lifetime for excess carrier lifetime for whole. So you take whatever you calculate, 4.5 times 10 to the power 4, you bring it down here. You divide by the lifetime, which means that before their lifetime is once they are created and destroyed, that's the lifetime. You divide by 2 times 10 to the power negative 7, then you get your recombination rate for whole. Okay, seems straightforward, not difficult. You just have to know that how do you calculate your PO. Okay, so you have to use this Ni square equation. You get this and you put your PO, divide by your time, you get your recombination rates. The second one, they're giving you delta N and delta P right now. What is the excess whole recombination rate in this condition? Over here, the recombination rate is that whatever they give you here, 10 to the power 14, you divide by the carrier lifetime, excess carrier lifetime, which is given this formula. Because there's no much information here already, you have to divide by what? Lifetime. And then you use this lifetime lah, and you get your answer. Okay, so complication comes with this. Sometimes in the later on example, they use this 2 here, and sometimes they don't use this 2, they use another time here. So students get confused which time you have to use. Are you going to use the carrier lifetime for excess for this or for that condition? But for this example, it is straightforward. Nothing difficult. So donor, maybe perhaps in the exam, you want to make it difficult, we don't tell you donor lah. We give you the name of this atom and you have to find out, is it, what is it? Is it a donor or acceptor? And then we don't give the word ND here because ND already give you a clue is donor. Example 2, let's look at example 2. Now they change to gallium arsenide. You got temperature 300, uniformly doped with acceptor impurity atom. Okay, Na is given here. Excess carrier lifetime is 5 to the power 10, which is about 500 nanosecond lah. Okay, 500 nanosecond. Okay, determine the excess electrons and hole recombination rate. If the excess electron concentration is delta n, what is the lifetime of hole? Determine the excess. Now they want excess electrons and hole recombination rate. Okay, they want the excess now. This one, they're not getting the excess. They want to calculate the lifetime of holes. Okay, then how do we do it? So now this fairly simple, 5 times 10 to the power 14, and then they already give you the excess carrier lifetime, and you use it, you divide, and you get your recombination rates. You get recombination for excess electrons and holes is the same lah. So you get this 10 to the power 21. Then the second part is that they want the lifetime of holes. So this given here is Na. You see, this is a bit me. This is a bit advanced a bit. So now you given you P equals to Na, okay. Then you calculate your NO, you use the Ni square equation, you divide, and you get 1.62. Okay, now you can get your PO and NO. Then they say that the lifetimes, what they want? They want the lifetime of hole. So you know that the recombination rates is actually for electron and hole, right? There's no prime here, and they want for hole. So we know that PO divided by TP or tau P equals to NO divided by tau N. And you got this information for PO and O. You got PO and NO now. Then the question give you the excess carrier lifetime. Excess carrier lifetime, what do you mean here? Tau N here, excess carrier lifetime. Then they got these three information because they want to calculate for hole. We assume this is electron. Then you multiply them and you get this answer. So there is one extra step lah, which is this part here. Oh, my one is not appearing. Where is it? Extra part here. The extra part here, you get this NO, PO here, NO here, and they want to calculate for hole. Then we find this information. Then we assume this is for electron, which is why they put this TNO here. We assume you put it down here, and you multiply it equals. So when it comes to this topic now, this you can say that the information are not much. So you have to do assumption because in here they didn't say that the excess carrier lifetime. They didn't say electrons or hole, right? Then you have to use this information and you calculate them. And that is why students find it a bit difficult because at first they thought that the carrier lifetime is the same. Then they say that, oh, carrier lifetime is the same, right? Because it's not that NO and PO is the same. No, carrier lifetime is not the same. The rates is the same. Rn and Rp is the same, but the lifetime is not the same. Oh, now another example 3 here. Okay, now let's look at this example 3. We got N-type silicon sample. We got donor, ND, all right. Minority, okay, the minority carrier hole, minority hole. So this is the N-type, okay, minority TPO equals to 20 microsecond. So what is the lifetime of the majority carrier electron? Okay, now it's given this minority here. They want to find the lifetime, the tau for majority. So electrons lah because N-type. The second one is they want to determine the thermal equilibrium generation rate for electrons and hole, which means that they want to calculate the G, the big capital G, N and GP. And this one is recombination rate for electrons and hole is R, big capital R, no prime, Rn or Rp. So first one is here, how to be solved for part A. So for part A, recombination rates are equal. This is similar the equation that shown earlier on here. So the ND is 10 to the power 16, correct? Then you calculate your PO, you use your Ni square equation, you calculate them, and then your carrier whole lifetime is, you just put in like the equation before, you plug in everything, and then you move around, then you get your T and not lah. tau. So anything extra? Yes, this is the part here. If you do not know this equation and also the ni square equation, you cannot do it. Okay, so don't suddenly in this chapter you introduce the EF minus EC or EC minus EF minus EV because there's no information on Fermi energy here. You cannot use that. You have to use the compensated equation. Then they want to find the thermal equilibriums. How do they do it? So just now the answer, they get 2.25. You get 2.25 here. They calculate, they get 2.25 for electrons and hole and divide by 20. Okay. So they get the G lah. Huh? Correct lah. We get for holes and divide by TP lah. Is hole. So generation equals to recombination rate. They say that. And that's why the answer is the same. Okay, another is critical thinking. Okay, so far, any question? Because this is more on the way that if you look at the example, is not difficult, but it's a lot of assumption. You have to think like this, you have to do like that, then you can get this equation. Not as easy as the chapter 4. You know that, oh, you got NO, you got PO, temperature changes. Okay, then you calculate. This one could be many types of question. So the only way to know is to try all the exercise here lah. Then you know what kind of question will come out, because the example I give you is only limited, is actually taken from this book here. But what kind of question that may appear in your, let's say if your final exam or test, you just have to scroll down and look at this exercise here, which is the one that we did just now. I think we did all these three here. It's actually from 6.1, 6.2, 6.3, right? Yeah, I think it's from 6.1, 6.2, 6.3, 6.1. 2006. 16 to 14. The end is about similar. Then that's the question they can ask. Okay, so the next part is they're trying to do the ambipolar equation, which is quite handful. Again, okay. Okay, the next part is actually the long winding explanation is because they would just want to get these two equations only. Okay, they say, okay, ambipolar equation 6.39. This is the general one, 6.39. Okay, ambipolar equation is actually this one, 6.39. And then they want to simplify it. Okay, 6.39. They can simplify it further, 6.39 for p-type in under low level injection becomes this one. They want to basically to get this equation what I can tell you. So to get to ambipolar equation, you got many components. One component is that you got the drift. Drift, you got mobility, right? You know that drift, you got mobility. Diffusion, you got dn here. So this one, diffusion, okay, you got mobility for drift. Then you got generation, and this one early on the first few slide that is shown, this is recombination for excess carrier. Okay, then in the end you get this d over dn over dt delta, the rate of change for excess electron. Before that, let's see what we solved earlier on. Something quite similar to here. This is one of this equation. This is the part here that we solve here. D over dt here. Okay. So the explanation, the long winding in the PowerPoint, also they read the Niemann's book, the objective is to get this equation. And when you get this equation, if they give you a certain steady states, or they give you in certain condition or environment, Then in this 6.55 and 6.56, you can cancel. You make it even shorter. So the condition simplification is if you say that, okay, give me the ambipolar equation in steady state. So you have to know what is the ambipolar equation here, the general one. Then you cancel it lah. You make it shorter. So that is what you're trying to do here lah. If you say steady state, then the time here it becomes zero lah because it's steady state. There's no net changes. Uniform, if you say it's uniform distributed, then this part here is equal to zero. And if you say electric field is zero electric field, then this is equal to zero, no excess carrier on. Carrier generation, then G prime is zero. Okay, G prime cancel equal to zero. And if it's no excess carrier confirmation, and delta T and delta P, T and PO become zero. Okay, so let me let you know first what we're trying to do. Then we get to the derivation part. So the derivation part here is, again, you see, this is quite long here. And in fact, I believe that I do not really need to actually write this slide here because once you look at the slide, you lagi pening. And bipolar, then create it, and cancel each other. Then this is the one that I show earlier on, and then in this condition here. Okay, so the first thing that you need to know what is ambipolar, okay, because this will be what is actually ambipolar equation. Okay, how does the excess carrier behave with time and space in the presence of electric field and density gradient? What is the effective diffusion coefficient and what is the effective mobility? This one will be solved this equation. To answer this question, we must develop the continuity equation for the carrier and then develop the ambipolar transport equation. Because by knowing the ambipolar equation, we can know that how does the excess carrier changes or behave with time and space when you give electric field, when they have non-uniform doping, when they have density gradient, different concentration level. And then in this equation, you also can get the diffusion coefficient. We covered diffusion and mobility in chapter 5, but here is called the effective diffusion coefficient and effective mobility. So what it meant here is that once you solve this thing here, they will get this dn. This is called the effective diffusion coefficient, and this is called the effective mobility coefficient. Yeah, this is the one. This is the one that in this ambipolar equation later on, you going to get the d prime and e mu prime, which is this one. This is called the effective diffusion coefficient and effective mobility equation. And how it looks like, it looks a bit like this equation. Okay, it looks a bit like that. So not to make you pening, is that this derivation step is just to explain to you what is going on, so that you can better answer the question. I would not ask you how to derive this equation because it's quite long here. But what I would ask is that pemahaman is what is going to happen to the electron, and if you see this, you have to know the final equation. And if I give you a certain condition, how do you simplify it? Okay. So if I want not to delve into here, let's look at Neiman's book lah. Neiman's book trying to solve ambipolar equation. We see. Okay, let's get back to here. Maybe it's much easier to explain from this part here. So what is important for your final exam and test is this part here. You need to know what is actually why we, okay, like I can ask you now, why do we need continuity equation? What does the ambipolar equation provides? That kind of things I can ask you. So you need to know why we want to use the equation rather than you need to know how to derive it, because I will not ask you how to derive this equation, how do you do this, but more to like, why do we need this equation? Why do we need to do that? So as mentioned in the beginning of this chapter, the excess electrons and hole, they are dependent on each other lah. That's what it means. It means that they diffuse and drift with the same effective diffusion coefficient, the one that I showed you, the d prime, and also the same effective mobility, the mu prime. And this phenomena is called ambipolar transport. So I ask you, what's ambipolar transport? So you need to be able to answer like this. They say that, okay, the excess carrier behave, how the excess carrier behave in time and in space in the presence of electric and density gradient, where they actually diffuse and drift with the same effective diffusion coefficient and effective mobility. And that is what called ambipolar transport. To do this answer, we must develop a continuity equation for carrier and then develop. So you say that in order to get ambipolar equation, you cannot just go straight to answer it. You need to do the continuity equation first, and once you solve something from there, then you can get the ambipolar transport equation. This is what it meant here. So the final result showed that for extrinsic semiconductor with low injection, okay, low injection, you already know, low injection means that the excess carrier is extremely small compared to the majority carrier. The effective diffusion mobility on the matter carrier, this is developed in the following derivation. Okay. So continuity equation for electrons and hole are developed in this section. It says that what they're trying to do is the differential volume element. Okay lah, just actually it's just like x and plus with delta x lah, the extra thing. So how did they get the continuity? They're gonna solve it, all this equation. But what we want to know is what do we get? So if you get this continuity equation in the end, they will get something similar to this part here. They got the force here, but it's almost quite similar to continuity again because this is the fundamental that needed. This part here, I think is same with chapter 5, okay, for Jn and Jp for this current density. Okay, then the current density put inside the continuity equation, they plug it in, they put it in here. And then they solve it. It's something new, similar to ambipolar already. Then what will appear here is that you will see something that the d, p, and mu lah, because this comes from chapter 5, the d and the mu comes from chapter 5, and that is why we got this coefficient. Okay, do again from this part. Okay, then they just sort each other lah. They want to simplify further. Note that equation 6.29 and 6.3 contain term involving the total concentration P and N and involving only the excess carrier D delta P and delta N. Okay, so this equation is somewhat similar to ambipolar already. And they say that for ambipolar equation, they say for electric field, they say that we got E apply and E turner, which is what it means here. If we got a thing here, we apply electric field. Like normally say we got a battery, you put it into a resistor, we got electric field, but there is also another one, internal electric field. So this is what ambipolar here. They say that, however, a third equation is required to relate the excess electron and hole to the internal field. Then they use Poisson equation. Okay. So this kind of question that I may ask lah, they say that what's the relationship between ambipolar transport equation with the one that the continuity equation that you derived earlier on? It says that the time differential equation, that continuity, they'll give you 6.29, 6.30, only describe the behavior of excess carrier. So you need another equation to relate these excess electrons and hole concentration to the electric field. And where you use Poisson equation lah. So, okay, they use Poisson equation, they relate to them. Then they take the continuity equation that just now. They divide, they do it. Then they will get something like these are 6.39 and 6. This is the one, 6.39. They say that this is the general ambipolar equation, which you can further simplify by using the term later on. And now here they say that the D prime, D prime and E prime, which is given by this thing, the effective diffusion coefficient and effective mobility equation. But now they call it ambipolar diffusion. Okay, so they get that part, Okay, this one you don't have to worry about that. Then, okay, the ambipolar for P type and N type, and then they simplify. Okay, so like I say, for this part here, the equation that I may give here, the equation that I give here, normally when I explain to student without reading Neiman's book, you'll find it a bit confusing. All right. What is important is need to know what is continuity equation used for, what is ambipolar equation used for, what's the difference between continuity and ambipolar, what is the connection, how do you change, how do you enhance it to ambipolar, and what does ambipolar give you. This one you need to know by understanding Neiman's book lah, more to like justification and also procedure lah, rather than ask you to write this equation and cancel each other lah. Look at this part here in continuity. Yeah, this is the ambipolar p type, and they get here. I don't want to move further for this quasi because this quasi is a different chapter already. This is a not different section already. I just want to focus on this ambipolar transport equation. So getting back to your test two, what I can say that if you were to ask you about chapter 4, we can ask you about compensated because we haven't asked that. We got this intrinsic. Chapter 5, we can ask you about Hall effect. Or then chapter 6 and 7, we can combine. Chapter 6 maybe ask you about a bit of theory, and chapter 7 is on calculation. Okay, so yesterday, there is an announcement that for your test and also for your final exam right now, you need to place your camera at the side rather than your face anymore, because they say that when you put on your face, you normally don't see what the student handwriting, you don't see how the student write, and you only can see the head. And sometimes they're talking, you cannot see that. So now the new procedure is that you need to put your camera angle on your side so that we can see what is your writing, what you are writing lah. And also for final exam, the exam will not be just 2 hours already. So question will be released per question already. So which means that if let's say that part A question maybe 45 minutes or 30-minute part A, then after that is over, then we go to part B, and then some question will be released. So students that decided not to, because some students say that I don't study for this question, and you just have to wait lah. It's not like in your final exam, oh, I don't want to answer question 1, I answer question 2 first, and then answer question 4. No, you cannot do that. Now you have to follow everybody already. Okay, this question, answer all question first, and that question lah. That's how it's gonna be lah. So for those that haven't scanned your attendance, I'll give the link here so you can scan now. And if you have any question on the Padlet, you can just ask me as well. Padlet, you just go in and you just fill it up and you ask question. No need to be so long. Ambipolar equation, chapter 6, rather than calculation type, more to understanding. Obviously, the earlier part is a bit easy lah, the calculation for this earlier part, the example 1, example 2, but the ambipolar is there's no equation, there's no problem like how to solve it in bipolar, very difficult. So maybe more to theory on that. Okay, so with that, we'll end the class today lah. Don't want to go on further. We already covered this, and then after that, we only got 2 more chapter, and then also I'll start preparing for your test 2 and also your final exam lah. For those who haven't scanned, you can scan now. So okay, thank you everyone. We'll end the class early today.
Doctor.
Yes.
May I ask for the for silicon and the current SI, the NI will be given in the NI slip or just state in the question, or you need to remember?
Normally the NI is you don't have to remember, it's given. So if it's not given in the question, they will give it in a table, and then for final exam student have to go pandai-pandai to go look at the list of appendix and find the NI lah. So if test 2 there's no table, then I have to give it in the question lah.
Okay, thank you, Doctor.
Okay.
But
Yes.
so normally the NI now will not only get from the PO and O, right? from the table, right?
Yeah, the NI you need to get rid from the table. Because in chapter
Also,
4, the NI we ask you need to get from the table. That's how you do it.
oh, okay.
Because in certain chapter earlier on, before we reach the table one, we ask you to calculate the NI yourself, right? So that's why you need to pandai-pandai lah. This question is from what chapter one? Then you don't go simply when you need to calculate yourself, you go take from the table. Then it's wrong lah. So that is so your question say when to use the NI from the table and when to use NI from calculation. You need to know your question. You need to understand what chapter it is from, so that you
How come why is it not same?
because the chapter 4 earlier on when you learn they haven't introduced the compensated yet right? Then you can calculate the NI lah. Once they introduce the compensated already, the NI you taken from the table. Because you cannot calculate the NI because right, first of all, how to calculate NI? You need NO and PO, right?
Yes.
Then when you need to calculate NO PO, depending on the question, if the NO and PO is actually from Venn diagram, then you can calculate NOPO, then you can calculate NI. But if the question doesn't have Fermi energy, then they only give you NO, then how you going to calculate PO? So you have to use the NI square equation. So you kena faham like that lah. You have to understand the technique
Oh, okay. Thank you, Doctor.
Okay. Okay, any more question? All right, no more question. I end the class. Okay, thank you.
Thank you, Doctor.